Hi and welcome to this Leaving Cert Applied Maths video where we're going to look at the basics of projectiles and we're going to look specifically at ordinary level style questions. If you want to move further and look at more higher level style questions, I've linked the video in the description below. So we're going to look at some projectile exam questions. So we're going to look at when the initial velocity is given to us in terms of I's and J's. We're going to look at what happens if a particle is fired horizontally. We're going to resolve the initial velocity so we can work with it, and we're going to work backwards to find the launch angle. So when we work with these, it's important to note this very strong link to vectors. Again, if you've not revised vectors or if you haven't looked at vectors, that will be worth going through first. So a projectile is when an object is projected, which means thrown with speed into the air at an angle to the horizontal. So we would have already met vertical motion where an object will be projected vertically, so straight up in the air. So when we talk about projectiles, they're going to have both a vertical and a horizontal component, which means when we approach these questions, we're going to break all of our information up into horizontal, which we call the x direction, and vertical, which we call the y direction. So when we think of the vertical component, so the y part, the only thing that's acting upon that is going to be gravity. So gravity is going to affect in a y direction only. In terms of the horizontal component, there is nothing affecting the ball's velocity. So that velocity is going to remain constant throughout the whole question. Now that sometimes feels a little bit strange and counterintuitive. So let's break it up to understand it a bit better. So let's take an example of a cannonball being fired off the cliff, and we have the velocity. Well, it's going to be fired horizontally, so there's only velocity in an x direction. So that velocity in x direction is 20 meters per second, and that's consistent the whole way down. What is changing is the velocity in a y direction. Gravity means it's going to accelerate. So it starts off with no velocity in a y direction, and that acceleration, so that gravity is going to start pulling it down, and it's going to go faster and faster, which effectively creates that curve. So when we talk about our x and y components of velocity in an x direction, nothing is changing. It has a constant speed. There is no acceleration. In a y direction, it's only affected by gravity. So there are some key ideas that you need to know for projectiles. These are the most important, but we will meet other ones as we work through examples. So the first one is the time of flight. So that's the time when the projectile lands, and it's usually the time when SY equals 0. I say usually because we are going to meet questions in this video where we're projecting an object from a cliff, and that's going to change where it lands. The range is Sx when Sy equals 0. So that is the horizontal distance after it lands. The maximum height will be Sy, so height in a y direction, when Vy equals 0. So just like when we were working in vertical motion, the projectile stops ever so slightly, so just for a split second, but only in the y direction. Remembering that Vx, so the x component of velocity, that is consistent. It is constant, there is no acceleration, so it's not changing. The last piece you need to know is that speed is the magnitude of velocity, and when we have the velocity vector, we can get speed by the square root of the x component squared plus the y component squared, all under the square root. We're still working with all our equations of motions, which come from page 50 of our log tables. So the first three there being the main ones: v is equal to u plus at, s equal to ut plus half at squared, and v squared equals u squared plus 2as. So the first thing I like to talk about when we look at projectiles is the link between projectiles as a section and quadratic functions. So our projectile, you can see the little diagram there on the right. When we throw something at an angle, what will happen is it creates this beautiful negative quadratic curve. And that's coming from the formula s is equal to ut plus a half at squared. So what I would suggest before you try to even start into projectiles is make sure that you are 100% comfortable with quadratics. So solving quadratics, we have lots of different ways to do. We have factorization. Within factorization, we have guide number or whatever way you solve quadratic trinomials. You can also use highest common factor. That could be a type of quadratic. We could use difference of two squares, and sometimes we may even have to resort to using the minus b formula. So when we talk about quadratics, and specifically negative quadratics, we have a maximum point, and that maximum point is going to be in terms of the projectile, where we stop ever so briefly, but only in an up and down direction. So when we think of projectiles and think of them in terms of quadratics, we can see that we actually have quite a symmetrical curve, and we can use that to our advantage, especially when we're working with ordinary level style questions. Think of the roots of the quadratic, so where it crosses the x-axis. We can take the x-axis as our starting point. So usually we don't take the height of the person throwing this into account. However, we do see questions where we're throwing it off a cliff, and we need to understand how that works. The purpose of this video is really to get to grips with the understanding of how to approach projectile questions. There are very specific ideas that you need to be aware of and be able to work with. As we move into the higher level questions, which, like I said, are linked in the video below, we're going to be working with the same ideas, but the algebra becomes a little bit trickier. So let's take a look at the 2022 ordinary level question. It was from question 3 part A, and we are given our projectile in terms of i's and j's. So when we deal with the projectile, what's important to note is that we give it a velocity in both the I, so horizontal, and j, the vertical direction. We have only one force that is acting on it, and that is gravity, or rather acceleration. So the gravity is going to pull down vertically, so it's only affecting this projectile in a vertical way. There is nothing that's affecting the projectile in a horizontal way, which means there is no acceleration in a horizontal way, which means we have no change in our velocity in a horizontal or I direction. So what we need to do to take account of these kind of, I suppose, different ideas depending on whether we're talking horizontal or vertical, is we divide the whole question into horizontal and vertical components. So we're going to go back to our linear motion, our VUAST, but when we work it, we're going to be working with VUAST in an x direction. Now time doesn't have a direction, time is going to be consistent. And then we have V in a y direction, U in a y direction, A in a y direction, S in a y direction, and T. So we're told that a particle is projected from point A on a horizontal ground with initial velocity of 25I plus 15J. So what that's giving us here, that's our U vector. So it's giving us the I, which is our x horizontal component, and 15J, which is our vertical y component. So let's fill that in. So we have 25 meters per second, and here we have 15 meters per second. So let's kind of just draw out what's happening here. So we project it up at an angle, I don't know what angle, and it will land again. So there's my lovely negative quadratic. I've now broken that U into x and y. The particle lands at point B. So here's our point A where it was projected from, and this is our point B, and that's a distance D from A. So we don't have a huge amount of information filled in, but we can now, using what we know, fill in the rest. So we said acceleration due to gravity is going to work down, but it's going to work only vertically. So we are working here in the y direction as minus 9.8 meters per second squared. If you were working at ordinary level, they take our acceleration as 10 rather than 9.8, but if you're aiming towards higher level, we're going to use 9.8 for all questions. So the next thing they're asking us to do is calculate the time of flight. So the time of flight is going to be this t here, or it could be this t here. Doesn't matter, it's going to be the same t. But the time of flight is when it lands at B. So we need to think, well, what do we know happens when it lands at B? So it has not actually traveled it hasn't displaced vertically because it's back to where it started. So SY is going to be 0 meters. So that's an important idea. The time of flight happens when SY equals 0. When we look in an x direction, it will have traveled d meters, which is what they have labeled A to B. There is no acceleration, so 0 meters per second squared, because we don't have anything affecting this projectile in a horizontal manner. And that means that our velocity is going to be the same at any point. Now, we can work in either an x direction or a y direction, but we have more information in a y direction, so we're going to work with that. We don't have a v, but we have a u, an a, an s, and a t, so we're going to work that out. So we're going to use the formula s is equal to ut plus a half at squared. So s is 0, 15 times t plus a half minus 9.8 t squared. And you can see here now we have a negative quadratic, so I'm going to actually just move my 0 to the other side. So we get 15t minus 4.9 t squared equals 0, highest common factor here, so we pull out our t. So that leaves us 15 minus 4.9t equals 0. We get 2 times, we get time equals 0, and we get time equals 15 over 4.9. Now, if we had used 10 here for our gravity, as we should with ordinary level questions, we would have got a really nice 3, but we got instead 3.06 seconds, which is our time of flight. The 0 is telling us the time it has not displaced horizontally, which also gives us the time it's at A, so that's t equals 0. But the time at B, which is the one we actually care about, that's the t equals 3.06 seconds. So let's fill that in, 3.06 seconds, and that's our answer for part I. Now, it then asks us for the value of d. Now, d is the distance between A and B after it lands. So now we can use the time that we've just worked out. We can plug that back in here. And we're then going to be able to work out d. So our time is 3.06. And now we're going to be working with all of these values here. Now we want s, so you want any formula that has s, so the best one to use will be s equal to ut plus a half at squared. So just giving ourselves a bit of space to do that, we're going to do s is equal to ut plus a half at squared. We want to find s, which they've labelled d. Our u is 25 times 3.0 times t, which is 3.06, plus a half. A is 0, 3.06 squared. Because we have no acceleration there, that's going to disappear. So our distance is going to be 25 by 3.06. What you're going to notice here is that when we calculate our distance is simply speed by time. And the reason for that is because in an x direction, so horizontally, there is no acceleration. So we follow our DST triangle from science at Junior Cert, or that, I suppose, simplified idea when there was no acceleration involved. Now, I wouldn't start kind of thinking like that, but I suppose it's, if you've noticed it, why does that happen? The reason is because there is no acceleration there. You're better to still follow your formulas. It will help you as they get slightly harder and as we bring in more algebra. So part 3 asks us for the maximum height of the particle above the horizontal plane. Now, when we talk about the maximum height, we need to understand when that happens. So the max height happens when it stops ever so slightly, but only in the y direction. So that's where Vy is going to equal 0. So let's work in our y direction. So we're going to do V, U, A, S and T. Now, the reason I'm writing these out again is because we're no longer working with kind of the full projectile path. We're no longer going to be, we're now only working towards that max height. So what do I know? Well, the initial velocity hasn't changed, so that's still 15 meters per second. I now know I want to find when it stops very briefly in a vertical direction, so that's 0 as Vy. Our acceleration hasn't changed, that's minus 9.8 meters per second squared, and I'm looking for Sy. So I can work with this. The formula I want doesn't have t, so it's going to be v squared equals u squared plus 2as. My v is 0, I'm squaring that, equals 15 squared plus 2 times minus 9.8 s. So 0 equals 15 squared is 225 minus 19.6 s. So s is equal to 225 divided by 19.6. So 225 divided by 19.6, and that gives us 11.48 meters. Now, that's not the only way that we could work. Because of the fact that this projectile makes a negative quadratic and that is symmetrical, we know that this maximum point here happens halfway, and we know the time of flight. So we do know the flight is time flight is 3.06. So this is 1.53, so you could have worked in terms of time there as well. Now, I don't think it saves us anything working with time, and if you've made any error in part I, you're going to follow that error through, while here for part 3 you've kind of started it fresh, so I suppose you're not going to save anything. Now, if they specifically asked us for the time that it happened, yes, that would mean a much quicker way to work than trying to work with a formula, but actually getting the height itself, it makes very little difference. So the maximum height is going to be 11.48 meters. So our final question here, IV, is asking us for the speed. Now, it's important to remember that speed is a scalar, it's a scalar number, which basically means we are dealing with simply magnitude. When we have a vector, that has both magnitude and direction. So basically what we're being asked for when we're asked for speed is the magnitude of velocity. And we have a little formula for that from our vector section, but let's work through it and see what we have. So the first thing I need to do is I need to understand my v as a vector, so with both I and j. Now the I is very straightforward because, as we said, the I piece actually doesn't change. That velocity is going to stay exactly the same because there is nothing acting in a horizontal direction. The j piece we're going to have to work out. So we come back to our v for y, uy, ay, sy, and t, and we need to figure out our velocity. They want it after 1.75 seconds, so let's fill that in. I don't know my s. My a is minus 9.8 meters per second squared. My initial velocity hasn't changed because I'm still starting this question at the same piece. And I'm looking for v. So the formula we're going to use for this hasn't got s, so v is equal to u plus at. So when I work that out, we get our velocity is equal to 15 plus minus 9.8 times 1.75, and we get minus 2.15 meters per second squared. So what that negative means, it's pointing down, so minus 2.15 j. So we're talking about 1.75 seconds. Halfway is 1.53, which means we're somewhere here. So the vector is moving like this, which is pointing down. which means I have a positive I because it's moving to the right, but a negative j because it's moving down. So that's negative is absolutely fine. I don't know why that looks like an 8. Let's change it back. So if I have my vector v, which is 25i minus 2.15j, I want to work out the speed, which is what they asked, which is the magnitude of the vector. So that is the square root of the I piece, which is 25 squared, plus the y piece. Now, it doesn't really matter if you bring in that sign or not, because we're squaring it, it's going to end up positive regardless. So this is a version of Pythagoras. You can draw it out if you want, but really you want to be able to work this relatively quickly. So if you can save yourself having to draw it out, that would make the most sense for you. This works out as 25.1 meters per second. So that's our speed. Be very, very careful with the use of speed instead of velocity, not to kind of think, well, that's the same thing. They're asking a very slightly different question there. So now let's look at a question where a particle is fired horizontally. So this is the 2015 ordinary level question 3, just the part A. So we can see in our diagram here that we have a cliff that's 80 meters. Now that's going to change how we approach our question as well. The particle is projected horizontally. So what that means in terms of our velocity, and our initial velocity, so our u is, it is given 14i and nothing in a j direction. Now, that's going to change because when we break this up, so let's break our VUAST into both x and y direction, AST, what we're going to find is that 14 is going to stay exactly the same. That doesn't change because there's no acceleration acting on this in a horizontal way. There's no forces acting on this. And in a y direction, we have gravity. So that is going to change that velocity as it moves. So we have a 14 meters per second here. We have 0 meters per second here. Our acceleration in an x direction is nothing. Our y direction is minus 9.8 meters per second squared. So horizontally is telling us the vector. It's telling us that there is nothing happening in a j direction. Now, when we start this off, we use that point of projection. Let me do it in a different color so we can see it a bit better. So this point of projection, we take that as the origin. So imagine my axis drawn in like that. So we're throwing that 14 along the x-axis or the y-axis if we're thinking in terms of vectors. What is important is when it lands. So in the last question, we said when it lands, it has no displacement in the y direction, so sy is 0. But here it's different because if we think of our point of projection back up here as our 0, 0, as our origin, where this lands is some number x, but sy is actually 80 meters below where it started, which is minus 80. So S, remember, is displacement, not distance. Very subtle differences. However, when we get into projectiles here, that difference is huge. It means that we can have negative displacement where we couldn't have negative direction or distance. We can also have the idea of after movement, S is 0, so that it hasn't displaced even though it has traveled a distance. So our SY here is minus 80. I have no idea what my SX is. That's actually the question. It says how far from the foot of the cliff will it hit the sea? So that's what I'm looking for here. That's my SX. And I'm looking for that SX when SY is equal to minus 80. So how we approach a question like this is we don't have enough information in the x direction to work out SX. We do have enough information in the y direction to work out either v or t. What we're going to do is we're going to work out the time when it hits the sea. And that time we're going to plug it back in here and then use that to get our SX. So it's kind of like our two-step process. So let's work in a y direction. I have u, a, s, and t. So I'm going to use s is equal to ut plus a half at squared. And that's going to be in the y direction. just going to label it y because we're going to use both directions in the one question here. So I have minus 80 equals 0 times t plus a half minus 9.8 t squared. So then I get minus 80 is equal to minus 4.9 t squared. So we can have 4.9 t squared is equal to 80. Now, if you want to bring this over and kind of do a difference of two squares, that's perfect. We're going to divide both sides by 4.9 first. So that's t squared equals 16.32. 3265, so that's 33. So to get time, we're going to square root it. Now, what we should do is put in a plus or minus, but we're only going to take the positive answer because we know that time has to be positive. So we get 4.04 seconds. Now, if I had used my acceleration as 10, we would have just got 4 seconds there, but we're working towards higher level questions, so we're going to keep that minus 9.8 and we're not going to round it to 10. So 4.04 seconds. And then we move that across here because time is happening the same in both the x and y direction. It doesn't have direction. So now that I've worked out my time, I go back and I work in an x direction and I want to work out my s. I'm going to use the same formula. So s is equal to ut plus a half at squared, and I sub it in. So I'm looking for s. My u is 14, my t is 14.04 plus a half times 0. Sorry, that should be 4.04 plus a half. A is 0 and then t squared 4.04 squared, but that's all gone because that's all multiplied by 0. So we get 14 by 4.04 and we end up with our s is equal to 56.56 meters, which is how far it is from the foot of the cliff. So our sx in this question. So let's look at a question where the velocity is not given in terms of i's and j's and where we have to actually resolve it ourselves. So this is the 2014 ordinary level question 3. A particle is projected from a point on horizontal ground with initial speed of 82 meters per second at an angle beta to the horizontal where the tan of beta is equal to 40/9. Now the first thing I'm going to do, regardless of what they ask, now they do ask for the initial velocity in terms of i's and j's, is I need to resolve that. So what we have here is a little right angle triangle that we're going to use to help us with the tan of beta. So let's put our beta in here, and the tan is opposite, so 40 over adjacent, so that's 9. And if we work through that, we can work out that third side, which is our hypotenuse. So we're going to have 40 squared plus 9 squared, and then we're going to square root the whole thing. So that's 40 squared plus 9 squared, and we get 41. And that is the length of our hypotenuse. Now, what that's actually doing is allowing us to work out the two missing trigonometric functions, which are, so I have tan beta, which is 40/9, but now I can get sine beta, which is opposite over hypotenuse, and I can get cos beta, which is adjacent over hypotenuse. So that little piece of work there helped me to work out sine, cos, and, well, I already had tan. Now, you could use a tan inverse. Problem with that is if you want to actually convert to an angle, you're going to end up rounding it. That's not ideal, because let's see what happens when we try to do this first part of the question and resolve. So here I have my projectiles, so that's 82. Now I wanted to, there's my horizontal ground, and it's going to go across like this. So I want to break this 82 into two components, its horizontal component and its vertical component. Now there's my angle beta. So this across the horizontal is going to be whatever my u speed is, so that's 82, and because it's adjacent, it's going to be cos beta. So again, this is something you've probably gone over when you're working with vectors. It's important to understand how to resolve it. But a vertical piece could also be placed there if it's easier to see in terms of a triangle, and that's going to be u. It's opposite, so it's going to be sine beta. So anytime we resolve our u vector, it's going to be u, which in this case is 82, cos beta, or whatever the angle is, I, plus 82 sine beta j. Now, because we're working with those lovely fractions, when we sub those in, we're going to get quite nice answers. So let me work just above it where I have a bit of space. So 82, instead of cos beta, we're going to put 9 over 41. And then here we have 82, 40 over 41j. And then when we work that through, we end up with 18i and 80j, so 2, yeah, and that is my initial vector u in terms of i's and j's. So if we try to work backwards and work out the angle, we're not going to get quite nice answers like that. So you really would need to be able to work with your angle as a fraction and work not just kind of with the angle itself, but taking the formula like here, so 40 over 9 being opposite over adjacent, working out the hypotenuse and working with it like that. So part 2 then asks us to find the time taken to reach maximum height. Now we know with maximum height that the particle stops, but it only stops in a y direction, so we know Vy is equal to 0. So let's work with our V UAST, but only in the y direction. So Vy Uy Ay Sy, and then time. Remember, it doesn't have a direction. So this is 0 meters per second. My u in a y direction is 80 meters per second. My acceleration, because I'm in a y direction, is minus 9.8 meters per second squared. And I'm looking for the time that it takes to reach that maximum height. So we have a v, a u, an a, and a t. So we want the formula that doesn't have s. That's v is equal to u plus at. And that is 0 equals 80 plus minus 9.8 t. So t is 80 divided by 9.8, which is just over 8. Again, we're using 9.8. In ordinary level, we tend to use 10, so that would be a nice, lovely answer. But for us, it's 8.16 seconds. Now, the next question, part 3, asks us to find that maximum height. So we're going to use the exact same layout that we've had. So that VUAST is staying the same. We now know our time, which is 8.16. You're going to get slightly different answer depending on which way you work this. We can go straight to S using t, so s equal to ut plus a half at squared, or you could go v squared equals u squared plus 2as. Doesn't matter. I'm going to work with v squared equals u squared plus 2as. That takes our previous answer out of it, so if something had gone wrong, you're still going to get your correct answer here. So that's 80 squared plus 2 times minus 9.8 times s. So that is 0 equals 6400 minus 19.6 s. S is equal to 6,400 divided by 19.6. So that gives us 326.53 meters. If you worked as s equal to ut plus half at squared and subbed it in, you're going to get exactly that same answer. So s is equal to 326.53 meters. Now part IV has asked us for the range. The range is Sx when Sy equals 0. Now because our projectile is projected off horizontal ground and it lands like this, we have kind of a full negative quadratic curve. we've already worked out that that maximum height happens when t is 8.16. So we can actually say that the time down here is 16.32 seconds. So we can use the fact that that quadratic is symmetrical to help us a little bit here. Now, if you want, if we hadn't worked that through, you could have worked the way we did in the last question, which is work out the time when sy equals 0 and then plug it back into sx. So this, we're only going to work in an x direction. So v, u, a, s, and t. Fill in what we know. We know 16.32 for our time. We want our sx. Our acceleration, there is no acceleration. Our v and u are going to be the same. They're both 18 meters per second. And my acceleration 0 meters per second squared. So I want a formula with s. The easiest one I think to use is s equal to ut plus a half at squared. And we can have s is equal to 18 times 16.32 plus a half times 0, 16.32 squared. That's all going to disappear. So the distance is just speed by time because there is no acceleration. And we end up with 293.76 meters. So that is our range SX. So 293.76 meters. So part 5 here, this question is asking us the 2 times when the height of the particle is 275 meters. So let's take a look at what the projectile looks like. So we project it up and it lands. Here's our horizontal. So we actually already know from a previous part that the maximum height is 326.53 meters. So we're being asked to find the height when the particle is 275 meters. So let's put that in about here. So we can see then why we're going to get 2 answers. So there's going to be a time on its way up, and there's also then going to be a time on its way down. Now, what we're being asked here is where is SY equal to 275? So anytime we're talking height, we're talking about a Y direction. So let's set up our V, U, A, S, and T. So our V, we don't know. Our U is going to be 80 meters per second, acceleration minus 9.8 meters per second squared. S is 275, and the time is what we are looking for. Now, what we're going to do for this is we're going to work using S is equal to UT plus a half AT squared. That's going to give us our lovely quadratic formula, which will give us our 2 answers. So we have 275 is equal to 80 times t plus a half minus 9.8 t squared. That gives me 275 equals 80t minus 4.9 t squared. We have a quadratic trinomial, so I'm going to bring everything over to the left-hand side to make it a positive quadratic, just to make life a bit easier to solve it. We're going to use minus b to solve this, so t is equal to minus, b is minus 80 plus or minus square root b minus 80 squared minus 4, a 4.9, c 275, and that is all over 2 times a, which is 2 times 4.9. We're going to get 2 answers, and both should be positive and both should be valid. So our first answer is going to be 4.92 seconds. And the second answer is 11.41 seconds. So they're the 2 times when the height of the particle is 275 meters above the ground. So now let's look at a slightly trickier question where we're actually working backwards to get the launch angle. Now, when we work with that, we're going to be working in terms of the angle. Now, this is very, very common at higher level, but less common at ordinary level. So this is a nice kind of preparation question before you move into work with the higher level questions. Trigonometry is a huge piece or part of the projectiles questions. So if you haven't already studied trigonometry in your Leaving Cert Maths course, you might want to leave the higher level questions until you have that covered. So this is the 2014 question 3, it's part B, and a golf ball is struck from a point or on the horizontal ground with a speed of 20 meters per second at an angle of theta to the horizontal ground. After 2√2 seconds, the ball strikes the ground at a point which is a horizontal distance of 40 meters from or. So find the initial velocity of the ball in terms of i's, j's and theta. So that's our first part. So when we're resolving, we're going to start with getting our vector, and it's going to be u, which is our initial speed, so 20. Our I direction is always going to be cos theta I, and then 20 sine theta j. And that goes back to how to resolve vectors, which you would have looked at in the vector section. We'll always, there's one slight difference, but for any of these questions, when we're resolving, cos will be in the I direction, sine will be in the j direction. So the second question is then to find the angle theta. So we're going to have to set up with our VU AST as we usually would. So let's start with our x direction. So V, U, A, S, and T. And let's also do that in the y direction. So VY, UI, AY, SY, and T. So we know that the u in the x direction is 2 cos theta, the y direction, 20 sine theta. The v in the x direction is going to be exactly the same because there is no acceleration. We were told that after 2√2 seconds, so let's work this question when time is 2√2, the ball strikes the ground at a point which is a horizontal distance of 40 meters from or. So if we were to draw that out, what we're talking about is that horizontal distance, which is Sx, so that's 40 meters. And we know at that time that Sy is also equal to 0 because it has landed. Our acceleration is minus 9.8 meters per second squared. So in order to find our angle theta, we can kind of work with either side. It doesn't matter. So let's work in an x direction first. So we need to make a formula, and we want to ensure that u is included. So we have it. Be careful, v is equal to u plus at is not going to be helpful because it's just going to say u and v are equal. So probably a better one is to include our s. V squared equals u squared plus 2as. We run into the same problem. So let's work with s is equal to ut plus a half at squared. So here we have s is 40 equals 20 cos theta times 2√2 plus a half 0 times 2√2 squared. Let's do a bit of cleanup. 20 times 2√2, which is 40√2 cos theta. Now I'm just going to flip this around. So cos theta on this side, it's going to be 40 divided by 40√2, which gives us 1/√2. And to work backwards to get our angle, we're going to use inverse. So cos inverse of 1/√2, and that gives us 45 degrees. So let's see how we could work this in a y direction. So we already have our answer, but let's see what we could do in a y direction. So we could use s is equal to ut plus a half at squared. We're going to have s is 0, so that's 20 sine theta times 2√2 plus a half minus 9.8 t squared, so 2√2 all to b squared. So tidying that up, we get 40√2 sine theta minus 4.9 at 2√2, so that gives us 4 times 2, which is times 8. So remember that we're going to have a slight rounding issue here because we're using 9.8, but they would have assumed that we're using 10 because of the ordinary level question. So what we have here is 40√2 sine theta equals 49 over 80 or multiply, no, this is 39.2. So then sine theta is going to be 39.2 over 40 root 2. It should have worked out as 1 over root 2 as well, but we have a little rounding because we're using our 9.8. So if we do sine inverse of, let's just leave this as is, let's not even tidy it up into a decimal. So into our calculators, we're going to do sine inverse. Just make sure you're in degree mode, especially if you've been working in radians. So we're doing sine inverse 39.2 over 40 root 2, and we end up with an answer of slightly off, but we get 43.8, so let's say 44 degrees. So we're 1 degree out because of our use of 9.8 rather than 10. So in a question like this, the better answer would come from the x direction, since we know that everything we've used in an x direction is valid for ordinary level, while we know that in a y direction we're using 9.8, so we're going to get a slightly different answer to what would be expected.